All right, let's talk about electronegativity and polarity. So, electronegativity is basically how tightly an atom is holding on to its electrons. And it has the same trend as ionization energy and electron affinity. So, it increases as you go up and as you go across. So, electronegativity increases going that way. Okay? So, you'll see all our metals, right? Lithium, sodium, let me zoom in here. Lithium, sodium, potassium, etc., etc., etc. Okay? These all have really small numbers, under 1, right? So 0.98, 0.93, 0.82. You'll notice hydrogen is 2.2. That's because hydrogen is a nonmetal. Okay? It increases as we go to the right. Lithium is less than beryllium. Beryllium is less than boron. Boron's less than carbon. Okay? Then we get to the heavy hitters. Fluorine is almost 4. Nitrogen is 3. Oxygen is 3.5. Chlorine's over 3. Bromine's almost 3. So you get the heavy hitters in this corner. And then pretty much all the metals are going to be relatively low. You'll notice that these metals, some of these transition metals, have relatively high electron density, kind of electron rich, right? You don't need to worry about too much about that. But really what you need to know is that it increases in generally speaking, as you go up and to the right. Like you might look and say, okay, between chlorine and nitrogen, chlorine is more to the right, but nitrogen is more up. So which is more important? Well, if you look at these two, it turns out that to the right is more important. Generally speaking, you're not going to need to memorize this, but what you do need to know is that the general trend of electronegativity. So how does this play out in bonds? Well, it leads to what we call bond polarity. So bond polarity is caused by a difference in electronegativity between two atoms. So electron density will be pulled from the less electronegative atom onto the more electronegative atom. And based on the difference gives you our different types of bonds that we've talked about: nonpolar, polar, and ionic. Okay? So if the difference in electronegativity is between 0 and 0.5, we call that a nonpolar covalent bond. So anything bonded to itself has a difference in electronegativity of 0, right? Even though chlorine has high electronegativity, it's what was like 3.16. The difference between 3.16 and 3.16 is 0. So anything bonded to itself is a nonpolar bond, even if it is a really electronegative molecule. Okay? So if it's between 0 and if the difference is between 0 and 0.5, that's nonpolar. If the difference is between 0.5 and 1.7, so for instance between hydrogen and chlorine it's 0.96, then that is a polar covalent bond. So you'll see from this electron density map, the electron density is being pulled up onto the chlorine. And then if it's greater than 1.7, then that's an ionic bond. So between sodium and chlorine, we've just kind of yoinked the entire, right? So you can see there's still like there's a transition zone, like a smooth transition zone here, whereas this is basically you have one sphere here, you have one sphere there, and they've kind of glommed together. Okay? So that's an ionic bond. So this is full positive, full negative, and this we would call partial. So we do lowercase delta positive, partial lowercase delta, that's an 8, lowercase delta negative. And then the way you draw it is you draw the dipole moment. That shows the direction the electron density is moving is a vector arrow, meaning this has that just basically means that this has a magnitude, and this is important because you can add dipole moments together. That shows the shift in electron density. So you have it's an arrow with a positive tail. So this is saying that this is the plus end, this is the minus end. So you have partial positive, partial negative charge. Okay, so that is a dipole moment for a bond. Okay, for a single bond, that's a dipole moment. Now, one important thing to know, because again, you probably don't need to memorize the whole electronegativity table, but one important thing that you probably do need to know is if we look back at our electronegativity chart and we zoom in, we see, okay, hydrogen's 2.2, carbon's 2.5. So a carbon-hydrogen bond is not a polar bond. So carbon-hydrogen is nonpolar, boron-hydrogen is nonpolar, but like oxygen, nitrogen, fluorine, and hydrogen are polar. Okay? So generally speaking, any of the halogens, nitrogen or oxygen, will form polar bonds. Generally speaking, it's not 100% true. So like carbon sulfur, nonpolar. Carbon oxygen, polar. Okay, so to get the actual truth of the matter, you would actually have to go and look at this chart. But the general trend is nitrogen, oxygen, fluorine, and the halogens will always form polar bonds for the purposes of Gen Chem. You may need to look it up on the chart sometimes, but for the most part, if you see carbon-hydrogen bond, nonpolar, guaranteed. But the other ones, generally speaking, assume they're polar. Okay. All right. So let's talk about molecular polarity. So this is talking about bond polarity. Now we need to talk about molecular polarity. So it's all well and good if a bond is polar, but how do we know if a molecule is polar? Well, you need to meet two criteria. So first, you have to have polar bonds. So methane, which is just carbons and hydrogens, right? Draw that. Oop, I need my pen. All right, so carbon and hydrogen. These are all nonpolar bonds, so this cannot be a polar molecule. So this fails to meet the first criteria. And then number two, it must be asymmetrical. But what that means is, remember, these are vectors, okay? So if you have something like carbon tetrachloride, these are all polar bonds, and the bond moment is going from the carbon to the chlorine. But all that will cancel out. So the net dipole moment is 0, which means it's a nonpolar molecule. Okay? So we look at water, for instance. Okay? Water has the dipole. So these blue arrows are the individual dipole moments. So these are the bond dipoles. And this is the molecular or net dipole. Okay? So the net dipole for water is shooting straight up between the lone pairs. Okay? And so because of this, you end up with a positive end of the molecule and a negative end of the molecule. This actually is what gives water its properties and gives you hydrogen bonding and things like that. You don't need to worry about that for now. But this is you have this point of asymmetry where if we cut along this bond, I have a hydrogen over here and I have nothing over here. Okay, so you have a point of asymmetry here. So that asymmetry is what leads you to a polar molecule. So polar bonds plus asymmetry gives you a polar molecule. Okay, if all the dipole moments cancel out, then the molecule is nonpolar. So for carbon dioxide, even though this is a polar bond and it's pulling towards the oxygen, pulling left, pulling right cancels out, so there's no net dipole moment. So this is carbon dioxide is nonpolar, even though it has polar bonds. One final thing. So the molecular geometries that tend to be polar are angular, trigonal pyramidal, bent, seesaw, T-shaped, and square pyramidal because they have asymmetry. So let's draw those out real quick. So angular, obviously, you have the lone pair, right? So that's going to give you asymmetry there. Trigonal pyramidal, like like ammonia. Okay, you see the asymmetry there. Seesaw, we looked at, like sulfur tetrafluoride. Okay. Bent, like this is water's bent, so I don't need to put another one there. T-shaped, what was the one we did? Well, whatever. Any T-shaped molecule. Very obviously, you have asymmetry here. And then square pyramidal, again, you have the square, and then you have the pyramid. So this point, the point on top, that's going to be giving you, so let's say, okay, so that's going to give you asymmetry, right? So if you assume that everything that's attached is a fluorine, because that's always going to be a polar bond, would it be polar? That's the question you got to ask yourself. One other thing to look out for is that asymmetry can be caused by the central atom being bonded to different elements. Okay, so if we go back to carbon tetrachloride, let me get rid of these notes. Boop. We look back at carbon tetrachloride. Okay, this is very polar bonds, but it's nonpolar. We replace one of these chlorines with a hydrogen. So this is carbon tetrachloride. That's chloroform. Oh, look, suddenly it's polar because this has 0 net. And now the net is pulling down because the hydrogen, this is nonpolar bond, this is a polar bond, okay? So asymmetry can also be caused by an asymmetry in elements themselves. So polarity is one of those things that's pretty hard to visualize, but basically if it has 0 lone pairs, it's probably, unless you have different things like this, right? If it has 0 lone pairs and everything that's attached is the same atom, then it's probably nonpolar. And so, first has to be polar bonds. Second has to be asymmetrical. So those are the things to look out for, and it'll just take practice.